Hello, everybody. Welcome to another discussion in dynamics. Today we will be talking about a lot of stuff, and I am not sure actually if we are going to do everything. So maybe without further ado, let's dive straight into our discussion. Okay. Today we will start with a brief lecture review, and then we will for sure do these two examples. I'm not sure if we will have time for the third one, okay, but we will see. And topic of today's discussion is normal tangential coordinate system. Okay. So today I would like to compare Cartesian, polar, and normal tangential coordinate systems. Yes, you guys know that these are three ways to describe the motion in 2D, maybe even in 3D. I don't know. We will see. So we have Cartesian, polar, we already know, and today we will talk about normal tangential. Okay, just to remind you, I know that I'm repeating myself for the, I don't know, 17th time this semester, yes? Cartesian coordinate system, what is characteristic about it? I and j, yes? Unit vectors that are constant, yes? That's it. How about polar coordinate system? We have UR, U theta, unit vectors again, but this time not constant, yes? They just follow our particle that goes along the trajectory. And today we will learn UT and UN. Okay, so the story goes exactly the same. The story starts exactly in the same way as last time. We have a particle following our trajectory. Exactly the same particle, exactly the same trajectory. Okay, and now we will define our UT and UN, which are again unit vectors, but not constant. They're not constant vectors. All right, so you can see that we define UT as aligned with velocity. So UT, in here, I even wrote it in here. Velocity is aligned with UT. So I can express the velocity in this way. V times UT plus 0 times UN. Okay, you don't even have to write it, yes? 0 plus times UN, yeah? Why I can express it like that? Because again, UT is aligned with our velocity vector. Any questions? Yeah. Okay, so now acceleration. Definition does not change, exactly as last time. A is equal to d dt of a velocity vector. So I can plug this guy here, v ut, and this is a product rule. d dt v ut plus v d dt ut. Okay, this guy, nobody has doubts that this is v dot, and this thing, believe me or not, is v divided by rho un. Okay? So let me write down the expression for acceleration. A is equal to v dot ut plus v squared divided by rho un. Okay, so these are our expressions for acceleration and for velocity. Yeah. Yeah. I skipped one part in my description in my talk, but before I'm gonna go back to my talk, the point I forgot. Are there any questions to what happened on the board, Trevor?
So in the Cartesian and polar coordinate system, we had a equation to describe position. Is there an equation to describe position in the normal tangential?
Perfect. This will be the second point I'm going to talk about. Yeah, thank you. Yes. Very good question. And by the way, you will tell me exactly what the answer is. You ask a question, but you know the answer. You're just not aware of that. You will help me on the board, okay? So I just would like to show other questions. Yeah, are there other questions so far? Think about questions, okay? And I will just continue talking. Hopefully my talking makes sense. Okay, so I just would like to show you guys why these guys are not constant, okay? Why they are not constant? Because this situation on this picture, let's say that this is situation at time instant, I don't know, 2 seconds, okay? 2 seconds. So let's say that at time instant 5 seconds, let's say at t 5 seconds, our point will be here. Our point P will be here. Okay? And this will be velocity of that point. Velocity is always tangent to the trajectory, by the way. So let us draw ut and un. Un always points inside the curvature, okay? So you can clearly see that ut changed the orientation, yes? Ut changed the incline, yes? Okay, at time instant, I don't know, 11 seconds, let's say, t 11 and a half seconds, our point P will be here, for example. Oh, that's not a good place for P. This will be a good place for P. Yeah. And our velocity will be pointing this way. Okay, again, ut is aligned with velocity, and un, I believe that curvature in here is like small, yeah, and it's that oscillating circle is here. Un will be here. You can clearly see, guys, I hope that you can clearly see that our ut and un change directions. Yes, that's why they are not constant. Yes, and that's why this time derivative is not 0. Any questions to what just happened on the board? Yeah. Okay, Trevor, ready or not? Let's go. Okay, so Trevor asked a very good question. How to express position vector in this coordinate system? There are 2 ways, Trevor. Yeah. Do you know the answer right away? Okay, I will give you some hint. Okay, please look at the drawing, at this drawing. Can you please sorry? Just give me 5 seconds. Can you please express point P that is here in that red coordinate system? How to express position of the black point in the red coordinate system? It is the origin. So what's the answer? 0, 0, 0. Yeah, exactly. It's 0. That's why we don't. And always, by the way, Trevor, similar question. Can you please express point P in this coordinate system? Exactly. It's always 0. Yeah, that's why we don't. So it's either 0 or we don't define it. Or we don't define it. Yeah. Thank you for help. Okay, I think that's all I want to say. Yeah. So, did you think of some questions? It is a little bit abstract. It is a little bit abstract, but you guys also have abstract minds, yes? So you are able to understand it, yes? Vince? Vincent?
If we don't define position, then we use another coordinate system for position.
Yes. For example, yeah, exactly. Yeah, yeah. This coordinate system is not used to define position because it is just attached to the point. Yeah. It travels with the point. Yeah. Okay. So what? Example number 1. Let's do it. So this is theory. Let's do practice. Okay. IJ. You didn't put your name, yes?
My real name is Aaron.
Aaron Jacob Johnson. Speed. Oh, sorry. Yeah. Oh, there's a different IJ here. Okay. Aaron Johnson. Okay, you are not here. Yeah. And Melina. Oh, it's fine. Yeah. Okay. Example number 1. Yeah. And by the way, if you are in this discussion, I know that I have transfer students from different discussions. Just put your name at the bottom. Is there any transfer student? Was your name not on the list? Okay, great. Please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? And by the way, IJ, this will answer your question from the previous discussion, okay? At the very end, I will answer, I will show you the drawing and so on, okay? So what do we have in here? We have our particle here on the rope, yeah? It is attached here, and that particle travels with a constant speed, yeah? So this is our trajectory, and velocity, as you can see, is constant at every time instant, okay? So that rope wraps around that cylinder. And yeah, so basically, for example, if particle is here, so I believe that the rope will be here basically, yeah? And velocity will be still v0 until our particle hits the drum, hits the cylinder. Okay, so we know that velocity is constant. We know the geometry. We know r and L0, and they also define angle theta here. Okay, angle theta here for us. And what they ask us for is to find acceleration of that particle. We should find acceleration in that particle in our new coordinate system. And once we find it in this new coordinate system, they ask us to bring it back to Cartesian coordinate system. Okay. So this is how I solve those problems. I just usually write down those expressions, those magical expressions from the previous board. Okay. But in here, we will actually just use expression for acceleration. A is equal to v dot ut plus v squared rho un. Okay, guys, I'm not even going to ask you, like, what is v dot? It is 0, of course, yes, because speed is constant, because v is constant. Great, that simplifies significantly our expression, yes, this is 0. Okay, so our A is v squared divided by rho un. Okay, let's plug in values. We know that v is constant, yes, so I can write in here v0 un, v0 squared, of course. And maybe some of you can tell me what is the expression for rho, how to find rho. Anybody? Based on this drawing, how to find rho? IJ.
Would it be L0 minus whatever segment is, or whatever distance is already wrapped around the circle?
Perfect, yeah. L0 minus whatever is wrapped around the circle. So the orange thing, this thing, yes?
Yeah.
Yeah. So what is the length of that arc?
It would be pi r squared times theta over 360, or 2 pi, whatever.
Almost there. This one, yes? You said that, but this is what you had in mind.
Yeah.
Let's agree to that. Exactly. Yeah. It will be r theta. Yes, this is the length of our arc, yeah, because our circle has radius r, and this is our angle, yeah, r theta. Yeah. It's much easier what you said, yeah. So that's it. Problem is solved. This is part A. That's it. Yeah. L0 minus r theta. That's all. So our A is equal to v0 squared L0 minus r theta un. Okay. So we found this is end of part A. Answer part A. Any questions? Yeah. Usually, some of you in the previous years, usually people ask me to explain one more time this. Yeah. So if you want me to explain it, just you can ask it. Yeah. Oh, sure, of course I can. Yeah. So what IJ said, he said that radius of curvature is equal to length of the rope. So at the beginning it was this, and with time passing, this will be our rho. So that will be like our rho, yeah. So this is like rho 0, yeah. And later, when particle is in here, this will be rho. Okay, you see the rho, or curvature of the trajectory decreases. Yeah. So he observed that at the beginning we have L0. Yeah, but with time it has to decrease. So there's L0 minus. This part wrapped around the cylinder. Yeah, because you can see, Vincent, that we started with L0 and the length of the rope didn't change. So after some time, rope will be this plus what is wrapped around. Yeah, it's the same rope. Yeah, so the rope will be this plus the orange thing. Yeah, so rho can be found from this expression. Yeah, I hope I didn't confuse you. Yeah, is it okay? Yes, and you are Christina. Yeah. One more time. Oh, no problem. Because for any circle, if you would like to find what is this arc, for example, what is the length of this arc? I don't know. Let's say gamma, or everybody's favorite delta. Let's say. No, I'm kidding. Gamma. Sorry, I have dark sense of humor. So if you know, Christina, if you know radius, yeah, and if you know that theta, gamma is equal to r theta. Easy. Yeah. Yes, sir?
Does it matter when the theta's in degrees or radians?
Radians. Yes. Is it Trevor?
Why are you measuring rho from the bottom of the length where it's attached to the barrel instead of the center of the circle?
Why? The easiest answer is because this is what it is, but let me explain it. You expect something smarter, yes?
Is it just because where the rope is attached to the barrel, that's where the, I guess.
This is the center of the osculating circle. Yeah. So velocity will be perpendicular to our radius. Mm-hmm. Do you see? Do you see?
Yeah.
So what you say is that, Michael, what you are talking, this is rho. No way, because this angle is not right. This is not 90 degrees. Do you see it? Yeah. It's like a method of elimination. Yeah. Nobody never asked me that question. I don't know like the super cool answer for that, super clear answer. But that would be like my physical understanding that velocity at this point must be perpendicular to the rho of that circle, osculating circle. Okay? So this is for sure not true what you said. This is for sure not true. Yeah. Okay, I can squeeze in one more question, or maybe two, which does not exist. Yes, they don't exist. Okay, so this is end of part A. Yeah, so we found our acceleration in anti-coordinate system. IJ, from the question from the last week. Yeah, so now let's draw it. Let's draw it again. Okay, and this is why you don't have to compute. This is why you don't have to calculate those unit vectors. Actually, you know what? I'm gonna draw it from scratch. So I'm not sure, guys, if you remember IJ's question from Wednesday, but he asked that do we have to calculate like the numerical values of those unit vectors? No, you don't have to, because when we have the drawing, we have the unit vectors. Yes, for example, right now I just draw this situation. Okay, I just draw that situation here. Yeah, we have the drum, we have the cylinder, and we have our particle on the rope. So we clearly see that UN has to be aligned with with that rope. UN and UT is here. That's why you don't have to calculate their values because they are on the picture. You can draw them on the picture, yeah? Okay, and now our goal, our task for part B, task is express A in IJ coordinate system. Okay, so first of all, let me draw I. So I will be green vector, and it will be it has only one component. Yes, this is our A. Sorry, this is our acceleration. Yes, it has only un, and our theta is here. So I think that they would like us to express A in this coordinate system, I and J. Yeah, so we must do these projections. We must do such two projections. We must have AX and AY. Yeah, we must find those two values. And to do that, I must bring this theta somewhere here. Yeah, I must bring this theta somewhere to the drawing. Okay, let me do it quickly. So I think I am able to do it. So let me first of all draw this direction, and maybe also this direction. So I claim that if theta is here, that means that 90 minus theta has to be here. So this is 90 minus theta. I claim that. Okay, what else do I know? Aha, I know that if this is 90 minus theta, this must be theta. This is theta. What's more, if this is theta, this is 90 minus theta. Okay, so theta must be here. Yeah, I brought theta to our drawing. Okay, guys. So AX is sine or cosine of A. A, sine or cosine? Yes. Sine theta. And AY has no other choice. AY has to be A cosine theta. Perfect. So I think that means that our A will be V0 squared L0 minus R theta sine theta cosine theta 0. But one thing is missing, yes? Please observe that AY points downwards. So I had to put minus in here. Yeah. So this is our A expressed in IJK. And this is our A expressed in UN, but also let's write it in a vector form. So A is equal to 0 V0 squared L0 minus R theta 0 in T and K. Yeah, these are just two exactly the same vectors, just expressed different way. IJ?
How does this work with the fact that the unit vectors change direction in normal-tangential and are constant in Cartesian? Like, wouldn't the unit vectors themselves have to have a transformation?
Yes, they have. Welcome to not this course. There are so-called rotation matrices. If you wanna learn about it, Google today or Wikipedia. You don't want to. Okay, so I will stop talking. I will stop talking. Yeah. Yeah. Are you a mechanical engineer?
Yeah.
Are you interested in robotics? No.
A little bit.
A little bit. So Google it today. This you will overuse them every day. Yes. Okay, guys. Any questions? To what happened? Oh, because A1 points downwards. Yeah. And I have to speed up, okay? Because we have, but feel free to ask questions, okay? I have to speed up because we are running out of time a little bit, okay? But before we move to example number 2, I would like to also draw this value, the magnitude. I would like to draw the magnitude of A, okay? So very quickly, let's draw that. A as a function of theta. So I believe that we start at theta 0, we will have V0 squared divided by L0. Yep, and this is a hyperbolic function. This is a hyperbolic function, so it will have asymptote here, and that asymptote will be realized at theta star equals to 0, L0 over R. This is A equal to V0 squared L0 minus R theta. This is that function. Okay, you can see that and this is heat, by the way. This is where heat occurs at this angle. Okay, any questions? Trevor?
What was the goal of drawing that graph was?
This?
Yeah, what was the goal?
This is just magnitude of acceleration. We did 101% of the problem. Yeah, this is magnitude of acceleration as a function of theta. Magnitude of acceleration as a function of theta. Okay. I don't hear any other question. Please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have our plane flying, and we are just going to model that plane as a particle, okay? We are just going to model that plane as a particle. And what do we know? Aha, we know that this is our trajectory. We know that this is our trajectory. This. And we start with velocity v0, which I, by the way, converted from kilometers per hour to meters per second. And we end up with velocity final, yes? And velocity 0 is pointing upwards, and our plane is taking turn right, yeah, turn right of 90 degrees. And it will end up with a different velocity at the end. By the way, velocity is not the only thing that changes here. Please observe that radius of curvature changes, yes? So we start with rho 0, and we will end up with a very small rho final, yes? This is that radius of oscillating circle. What else do we know? Aha, we know something very, very good. I mean, that will make our problem more easy. So an is constant, and an is equal to 8g. And also they told us that speed decreases uniformly, which we will use in a second. You guys, I will ask you to translate that in a mathematical language, okay? In more mathematical formalism. And what they ask us to find? They ask us to find what is the radius of curvature at the end, rho final, and how much time does it take to take that turn? How much time the plane needs to take that turn? Okay, solution is following. I just am going to write down this expression from our previous board. So that would be v dot ut plus v square rho un. And by the way, this is equal to at ut plus an un. Yeah, we have our accelerations in tangential and normal directions. So I can write in here that AT is equal to V dot or dv dt, yeah, and our AN is equal to V squared over rho. And I would like to use the second expression to solve part A. Solve part A. Okay, because they told us that AN is constant, yes? AN is constant. And this is equal to 8G. So we can write 8G is equal to V squared over rho. So we basically found expression for rho, because rho is equal to V squared over 8G. Rho, all of a sudden, is a function of velocity. Yeah? So, question to you, maybe some of you would like to help me. How to find rho final? This is what you had in mind. Exactly. So rho final is that function with V final. Exactly. Rho final is V final squared divided by 8G, sorry. Plug in values. This is a funny number, by the way. It's 222.222 squared, 8 times 9.81. Grab your calculators, and you can obtain. Oh wow! I was solving this from memory. It looks like. Yes. Where are my solutions? Yeah. Give me a second. Interesting. Oh yeah, I was so far I was solving everything from memory. Interesting. Okay, but I don't remember that number. So that is approximately 6 to 9.238 meters. Okay, we killed part A, yeah, like champs. Exactly. I like that, Brian. Yes, I like that attitude. I like that approach. Answer A. Okay. By the way, what shall you do to find rho zero? Yeah, just plug in velocity of zero. I don't know. I didn't do it at home, and they didn't ask us for that. You can do it at home if you want. Rho of v0. Great. Okay. Any questions to part A? Part A was easy, by the way. This is easy. This is harder. This is easy, in my opinion. Of course, you don't have to believe my opinion. This is easy, but this is harder. So let's do part B, okay? And we have 16 minutes. I think we are able to do it. Now, part B. Find T final. Okay, so I think that in part A, if I scroll up the board, we used this expression, yes? We used this expression. So how about using this guy in our part B? Let's use the other guy in part B, okay? Let's do it. So I can write in here AT is equal to dv dt. And I want to integrate. I would like to integrate. So I will have dv on this side and AT dt. However, we do not know what AT is, but we can deduct something. Can you guys tell me something about AT? What information we know about AT? Yes, thank you for reading. That's a very good ability, yes. But what does it mean mathematically, Vince?
Oh, it decreases for the constant
Okay,
acceleration constant.
that's what you had in mind. Yes, exactly. So yeah, exactly. Thank you, guys. Yeah. So this is constant. At is equal to constant. Why we know that? Because speed decreases uniformly. Decreases uniformly. Okay. Do you like integrating constant stuff? Easy. Yeah, that's good. Yeah, that's good observation. Really simplifies the problem. So we're gonna integrate that, and maybe so I'm gonna put integration bounds in here. Okay. So at time instant 0, I believe that we start with v0, yes, and at time final tf we will end up with vf. Okay. So that was easy. So if we integrate that, we will end up with vf minus v0, and this will be at tf, right? So that means that tf, the unknown they are asked us to find, is equal to vf minus v0 that we know, but we unfortunately don't know at. We don't know at. So now our goal is to find at, and we can call it a day. Yes? And you guys can go to Chicago. Really? That was funny? Come on. I have better jokes than that. Okay. Okay. Do you see that? We know everything. They told us what is VF. They told us what is V0. They didn't. We don't know AT. So I would like to ask for help or question or help.
Yeah, if it like decreases uniformly, and it well, never mind. Because you don't know the time, but you know the change in velocity, so can you use that because it's a linear acceleration?
Yes, but your previous sentence, we don't know the time also. Yeah, if we knew the time, we know acceleration exactly, but we don't know the time, unfortunately. But don't worry, there is another way to find it. Yeah. Any questions? Any idea, guys? How to find AT?
Like the other coordinate system, NT, or no?
Oh, we are using it all the time. Yeah. Polar. We can do that, and I think we will do it. Yes, but we will do it like implicitly. We'll do it implicitly. Yes. I'm just now wait a couple of more seconds, okay, guys? Do you have anybody has any idea? It can be even a bad idea. Don't worry. Who has like the worst idea how to solve that problem? Yeah. So I'm gonna give you a hint, okay? And maybe I'll even gonna tell you what to do. So far we integrated in time, yeah? We integrated in time. So, but this is not the only thing we can do. We can also integrate along the path. Yeah. So how about now integrating along this curve? Let's integrate along that curve. Yeah, and let's see what will happen. Let's now integrate along the path. What do I mean by that? So I'm going to use exactly the same expression as before. At is equal to dv dt, but we're going to do that little trick we did recently. dv dt, and I'm going to put ds in here and ds in here. And we'll end up with v dv ds. Okay, let's integrate right now. Yeah, clearly I'm going to integrate along the path. Okay, so let's do it. So we will have v dv, maybe again, and right now we have at ds. But this causes problems, yeah, because unfortunately we do not know How long is this? Yeah, we don't know that length. If we knew that length, we could do it, but we don't know how long is this distance. Yes, but we can maybe use Michael's digression number one. Okay, so digression number one. Digression number one. ds is always rho d theta. Always. Okay? And I'm gonna put a drawing here, okay? Just so that you know what is ds and you know what is rho and you know what is theta. So let's imagine that we have arbitrary trajectory. Arbitrary trajectory. Yeah. By the way, is the font size too large? Or is it okay? Yeah. Okay, and let's say that our point P is here. And in a second, our point P, oh, sorry, I can lift it there. Yeah. Our point P will move a little bit here. Yeah. ds is so-called infinitesimal increment of path of trajectory. Yes. Our point P will move there in a second. Okay, so let's now draw our osculating circle here. I think it will be big. Yeah, this is our osculating circle. Osculating circle. We have our rho at that point, and we can also draw something like that. This is our increment in angle. This is exactly what Christina asked like 5 minutes ago. Yeah, so that arc. So ds is exactly radius times angle. Yeah. So I hope guys that this drawing explains why this is always true. This is always true. So we can plug it in here basically. Do you see? We can plug it here, and we will end up with v dv is equal to at rho d theta. And now yesterday when I was solving that, I asked myself, what on earth is rho? What is expression for rho? Because we don't know how rho changes. Yeah, we just know rho zero and rho final. However, 10 minutes ago, we found this expression. Yeah, we expressed rho as a function of velocity. Do you remember? Let's use this one. Let's use this one, and we know and we can integrate them. Yeah, 5 minutes ago, this happened. So now we can basically plug this guy here. And we end up with v dv is equal to at v squared 8g d theta. V squared appeared on the right hand side. Everything with v should be on the left hand side. Yes, I have to bring it there. So we will end up with dv over v, and this is equal to at 8g d theta. Now we can integrate. Okay. So I think that we switch from v0 to v final, and maybe somebody can tell me what are the integration bounds here, how theta changes. 0 to pi over 2, perfect. Yeah. 0 to pi over 2. Yeah, and this thing is constant. So we will end up with logarithm natural of v final minus logarithm natural of v0. This is equal to at 8g pi over 2. And this can also be simplified. I believe that if we subtract one logarithm from another, it can be actually this. Logarithm natural of v final, v0. Yeah. Okay, so let's find at. At is the only unknown in here. At is 2 over pi 8g log natural V final, V0. Plug in values, 2 over pi times 8 times 9.81 times log natural. In here doesn't matter which units you're gonna use. I'm gonna use 8001100 because those units will cancel out. Grab your calculators and obtain that our AT is approximately minus 15.91056 meters second square. Okay, we obtained a negative value of AT. Does it make sense? I think it makes sense because velocity decreases, yes? We start with 1100 and we end up with some smaller number than 1100, yes? It makes sense. AT should be negative. Okay, so now let's just find the final thing they ask us for. T final was equal to VF minus V0 divided by AT. Plug in values, this time in meters per second. So that would be 222.222 minus 305.556 divided by the value we just found, minus 15.91056. That would be approximately 5.238 seconds. This is how much time plane needs to take that turn. Answer B, and 100% of the problem done. Okay, guys, we have 3 more minutes. How does it look like from your perspective? I see one head nodding, 2 heads nodding. Okay, it is, as I said earlier, this is complex, this is abstract, but you guys have abstract brains, yes? You are able to do it. Any questions? Before you go, do not pack your stuff in. I still have you for 2 minutes. Yeah. So we didn't do one problem, okay? We didn't do this problem. Yeah. Attention, please listen to me, okay? Please look at that problem at home, okay? Solution will be at Canvas, yes? Why do I want you to look at it? Because this problem illustrates how to use this expression. Rho is equal to, and I just don't know if this expression will be on the final or on some exam. Yeah, so I just would like you guys to know that such thing exists. This problem illustrates how to use this formula. Rho as a function of x, 1 plus y prime squared, square root, to the power of 3. And in here we have y double dot absolute value, okay? If you solve that problem, if you look at the solution, you will exactly know how to use this formula, okay? That's why I think it's important to look at that problem, okay? Unfortunately, we didn't have time today to cover that. It's a short problem. So what? Thank you for today and enjoy your weekend. Bye.